Welcome to our project of self-calibrating CMOS image sensor-based visible light spectrometer. Our team members are Christine Wong, Brad Steve Hua, Sibeli Montero, Kia Tuan Nguyen, Chanel Romero, and Newton Wei. And our advisor is Dr. Rita Olson. We'll talk about what spectrometers are and our focus for this project regarding them, how we built it into components, the software we designed for it, how we captured the images, the calibration techniques, and the analysis of the spectrum and the results.
Hello, my name is Stephen. Today I'll talk about the background of the spectrometer. A spectrometer is an instrument used to measure the intensity of light over a specific range of electromagnetic spectrum. There are three types of spectra: continuous, emission, and absorption. So how does a spectrometer work? So first of all, light passes through slit, which may be installed a filter to control the width of the slit. Then the light transmits through a biconvex lens to make it more focused on the focal point, because the light waves parallel and coherent. It goes to a diffraction gradient, which is split photons by wavelength. The diffraction gradient then directly spread light on the camera detector. So the individual pixels of the detector are recognized by the transmitted light. So each pixel represents a portion of spectrum which is translated into an answer with a custom software. So our team's objective is to design a low-cost spectrometer because the spectrometers which is selling in the market are more expensive. So in this slide, I'm going to talk about abstract. So a visible spectrometer is designed and implemented featuring low-cost, readily available components. The spectrometer is configured through a custom software interface, which allows users to perform self-calibration optimization on the acquired spectral data.
Our spectrometer design requires only a handful of components. An enclosed box made of medium density fiberboard houses a biconvex lens, diffraction grating, optical zoom camera, and razor blades placed parallel to each other to create a narrow slit. At a distance of the focal length of 5 centimeters, the biconvex lens is mounted behind the slit. A diffraction grating of 1,000 grooves per millimeter is placed parallel to the lens of the optical zoom camera, and the two components are then positioned at an angle behind the biconvex lens as illustrated. In order to target the full visible light spectrum, all of the components are carefully adjusted to achieve the highest resolution from the view of the camera. In order to analyze a light source, the slit allows a small amount of light to enter the box. Given how narrow the slit is on the front of the box dictates how sharp the emission spectrum becomes. The biconvex lens ensures that as much of the parallel light from the slit converges to hit the diffraction grating. For this project, a compact fluorescent light was used to calibrate the spectrometer. Red, green, and blue lasers of known wavelengths were used to determine the accuracy and precision of our design. In the following demonstrations, we see that the lasers are pointed perpendicular to the slit, and the CFL and LED bulbs are adjusted so that the camera detects the full intensity of each light source. It is important that there are no moving parts to the design. As we can see through the demonstration, any movement or the slightest change in placement of any component can drastically distort the image. The optical zoom camera is connected to a computer via USB, in which the graphical user interface can adjust exposure, calibrate the spectrometer, and analyze the unknown emission spectrum.
My name is Newton Lei, and I will be talking about the custom software we developed. We designed a GUI that would allow users to easily collect and analyze spectral images and data from the spectrometer. With our design, we wanted users to be able to see a live webcam feed capture, save, and analyze spectral images from that webcam feed, and from there generate data and put it into an Excel file that they'll be able to examine later on. To create the interface assignment, you use PyQt5, which is a set of Python bindings for Qt. Qt itself is a set of libraries from which we use mini widgets to implement the various visual features and the layout of the GUI application. For the other functionalities like image processing, graphing, and calculations, we use OpenCV, scikit-image, matplotlib, NumPy, and SciPy. On the next slide, we will go more in depth on the interface functionality.
Hi, I'm Sibeli, and I'll be explaining a little bit more about the custom software. Here in this slide, you're able to see the final application wireframe and user flow. The final application has 3 tabs. The first tab is the About tab. It contains over information about the project and asks the user to choose a safe location for the pictures to be taken. Next, we have the Capture tab. The Capture tab is responsible for image capturing, calibration, and spectral analysis. Lastly, we have the Analysis tab, in which the user can see the results of the analysis. The user can save this data into an Excel file by pressing the Generate Report button. On the next slide, you'll be seeing a live demo of the software. Here, I'm opening the terminal and writing the path to find the file, the Python file. The program is all written in Python. Here, you'll be able to see the first tab, the About tab. And the first step we need to do is choose a save location to save all the pictures. And I've already set up the blue laser in the spectrometer. So it's ready to see the image on the webcam. Now we're seeing the blue laser and we're starting calibration. We pick laser because it's the type of light source we're using, and we need to input its color and wavelength. Calibration must be done with 3 lasers and a fluorescent light. So we're going to be repeating this process. The next picture, and I'm setting up the green laser. Pressing calibrate one more time, input its light color, which is green, and the wavelength length, which is 532. The next picture, we're going to see a red laser. Input its information, light color red, and wavelength is of 650 nanometers. The next light source will be a fluorescent light that I'll be setting up on the spectrometer. And we'll be inputting its wavelengths and color. The color for the fluorescent, it's fluorescent, and we're putting all the wavelengths present in this spectrum. Next, we are done with calibration. The program's confirmed so we're done and ready to analyze the spectrum. We'll be analyzing the spectrum of an LED light source. And now we're in the Analysis tab. We're able to see the spectrum image, the intensity plot, and its wavelength. We're generating a report, and I'll be saving in the same place with the other pictures, but you can save anywhere. And next, you can go back to the Capture tab and analyze another unknown spectrum, or you can exit the program.
So I will talk about how we capture the image and what problem we have faced when we capture image. Picture we take in this slide are the same exposure tab. As you can see, we took three different lasers. The blue one, the green one, the red one, which is represent the color in the spectrum. As we can see, the color of the laser color under exposure, and even though we can use it in the analyze, but it's kind of dark. And when we took the fluorescent light capture, the blue line is kind of underexposure, but the red line, the red and yellow line is kind of overexposure. So we need to have a solution so we can balance the underexposure and the overexposure in the fluorescent light. So the source we're given is we're using the exposure fusions. So exposure fusions is a method for combining image taking with different exposure setting into one image that look like a turn map high dynamic range image. When we capture a photo using a camera, it has only 8 bits per color channel to represent the brightness of the scene. However, the brightness of the world around us can vary from 0 to almost infinity. And when you look at the image in the slide, we took 16 different exposure picture, 16 different exposure time. And when we combine it, we have this this picture. It's very dry and lively. So how it works with our laser and fluorescent light. So with the laser, the light in with the laser, because the laser has a high intensity, so we use very low exposure time. For laser, I believe I use 6 different exposure from -13 to -11 to capture the laser image. And so this is picture after the exposure fusions for the laser. It appears to be brighter and it's easier to detect and analyze. For the fluorescent light, the colors in every spectrum appear brighter, and we are able to see it clearly.
To use a spectrometer for mapping a spectrum from an image, it needs to be calibrated to provide an optimized function. For this system, there are 2 ways to calibrate the spectrometer, with a linear or a cubic curve. The linear calibration uses 3 images from lasers of known wavelengths. For example, there could be a blue laser, a green laser, and a red laser with the wavelengths of 405 nanometers, 532 nanometers, and 650 nanometers respectively. The other method is using a fluorescent light as calibration. Based on the peak intensities, we can approximate appropriate X values and wavelength values to find a fit. Along with the laser calibration, the resolution of the design can be estimated using the full width half maximum for each laser. Let's begin with explaining how the linear calibration works. As it can be seen by the image labeled 1, laser images, it illustrates the spectrum of the laser that is captured. We need to determine the center of the images. Thus, OpenCV supplies a Canny function. The Canny function is a multi-step function that maps the edges and contours on the image. Image 2, called Canny edge, is an example of grabbing the outline of the laser images. A NumPy array is created to store the coordinate values of the spectrum. With the edges of the image, it allows for simpler analysis of the minimum and maximum coordinates, or X and Y values. The center pixel points are found by taking the average of the maximum and minimum pixel coordinates. With the 2 pieces of information, known wavelengths and center X coordinates, a linear fit can be found with the dataset. However, it should be noted that there are inherent inaccuracies with the linear curve because the lasers used have a potential 10 nanometer error. Moving on to the nonlinear calibration, another way to calibrate the spectrum is to use a fluorescent light. In the figure called original spectrum, it maps the pixel intensity versus the pixel position. As it can be seen, there are multiple spikes observed in the original spectrum based on the yellow marks. However, the graph is noisy, resulting in extra spikes in the graph. To smooth the graph and reduce the noise, the data is convolved with a Gaussian. The next figure, CFL spectrum, shows the convolved graph and fewer spikes detected. With a smaller set of spikes, the intensity at the peaks can be used to determine the X coordinates of the peaks. similar to the linear calibration, given the known wavelengths and the x-coordinates at the peaks, a cubic fit can be determined. Now, to estimate the system's optical resolution, the laser images can be used. Taking the laser images, they are fitted to a Gaussian. Then, the points that are at half of the maximum value are stored to find the width at half of the maximum. The full width half maximum can decide which wavelengths can be resolved with the current system. Now, the next part, the spectrum analysis and results, will be explained by Grant.
Thanks, Christine. Our original objective was to create a visible light spectrometer that spanned the entire visible region from 400 nanometers to 700 nanometers. Unfortunately, we don't have any clear spectrum lines close enough to 700 nanometers for an adequate calibration. As shown previously, the largest fluorescent wavelength used in the calibration is around 611 nanometers. We chose to extend our range up to 650 because we used a red laser in determining the resolution. The typical spectral resolution of the device was found to be around 1 nanometer. This means our spectrometer can identify distinct wavelength or color lines as long as they're 1 nanometer apart in the spectrum. The number of detector pixels used is an important variable in determining that spectral resolution. The more pixels used for a given range, the better the resolution will be. In our design, we were able to utilize 1,521 pixels, or about 80% of our camera's total pixels. This utilization of pixels was limited by our ability to align all of the components inside of the spectrometer. When it comes to repeatability or precision of results, users can expect a maximum standard deviation of 0.4 nanometers from the mean. However, this precision improves significantly to plus or minus 0.2 nanometers for most of the spectrum between 400 and 611 nanometers. This is due to the fluorescent peaks that we used during the calibration. In the end, the entire project cost us $102. Now, our design is far from perfect, and there are some things we would like to change. One design modification is limiting the angle that light can enter the slit by placing a small aperture in front of it. We believe, based on test data, that this would improve precision. Certainly, it would improve spectral resolution measurements where consistent laser angles play a role. Another modification would be a smaller collimating lens. If we want to make the device more portable, then we need a focal length much smaller than the 5 centimeter focal length used in this project. Something that was largely ignored during this project was an analysis and calibration of light intensity. Light intensity calibration is required if you want to know the concentration of a source. Without it, our intensity analysis is completely qualitative. We also limited ourselves to emission spectroscopy, but perhaps more useful is absorption or even fluorescence spectroscopy. Testing these methods should still be possible with this design. It simply required more material and time than we had available. In conclusion, our team met objectives by creating a light spectrometer that spans over 90% of the visible light spectrum. We also created custom software that allows anyone with CMOS camera to capture an emission spectrum. The device's resolution and precision are comparable to devices costing many hundreds of dollars. Our spectrometer may not be as portable as those industry designs, but it does demonstrate that modern CMOS cameras can be used to analyze a visible emission spectrum. Most excitingly, it indicates that future development of a portable version using cell phone cameras as the detector is possible. The creation of a phone attachment along with self-calibrating software could benefit industries including astronomy, education, food, and drug safety. Further experimentation is definitely worth exploring. Thank you.